Today we're going to talk about some friction problems. Before we jump into an example, I want to point you in the direction of some clarifying points. In the book, section 8.2, definitely should review the important points. So friction is going to resist movement of one surface relative to another. If there's no sliding, the maximum is the coefficient of static friction times the normal force. If there is sliding, then the friction force is the kinetic coefficient of friction times the normal force. And there are several types of static problems where we need to draw the free body diagram, apply the equations of equilibrium, and then satisfy conditions of friction or tipping. Procedure for friction problem solving: free body diagram. Always start with the free body diagram. You do want to show the frictional forces as unknowns. You don't assume that F equals mu n, unless it is directly stated that we are at impending motion, or if it's stated that slipping occurs. Look at the number of unknowns, compare it with the equilibrium equations. If there's more unknowns than equilibrium equations, then we have to have some additional frictional equation. Over here, on the right-hand side, this is from the procedures and strategies at the beginning of chapter. In the worked examples, it's chapter 7. In the textbook, it's chapter 8. But the procedures and strategies for friction, very, very similar to what it says here in the book. Draw the free body diagrams, make sure friction opposes impending motion, write the equilibrium equations, and compare the unknowns and the number of equations. Really important in both of these, making sure that you don't assume that F equals mu n unless you're explicitly told that it does. So 2 good resources available to you, one in the textbook, one in the worked example procedures and strategies. Okay. Here we have a block that's 400 pounds, and there's 2 wedges that have a negligible weight. And we're using those to position the 400-pound block. The reason wedges are nice is that it's going to help us reduce that amount of force needed to lift it. So instead of 400 pounds needing to press straight up, we're going to be able to use a lower force pushing sideways, which is easier to lift that block. So we've got a couple of free body diagrams we can draw. We're going to start with essentially, we'll start with the wedge. And this wedge has this angle of 10 degrees. So we know that we have a pushing force P and a normal force at the ground. There is no weight here. Let's call this, actually, I'm going to rename this. I'm going to label my body to have these contacting surfaces, A, B, and C. And now I'm going to change that up. So this is my normal at A, and this is the normal force at point B. For this first free body diagram, I'm really just isolating that bottom wedge, so I don't see the 400 pounds. It's not applied onto this wedge. Okay, the second free body diagram, when I'm working on friction, I like to have both of them going at the same time, because sometimes it's easier to see what's happening on the other block. So the second free body diagram here is actually both of these. Undo that. Good. Okay. Here we have 400 pounds down. We have the equal and opposite normal force at B. And it's also sliding up the wall at C. So if you weren't sure about what the contacting surface at C was, if you take a look at this second free body diagram, the normal force at B does have a rightward component to it. So there's a little bit in the x direction, so something has to resist that motion. So the wall is going to have to push back. All right, so the goal is that P is pushing to the right, so friction is going to resist that rightward motion. And I'm going to have friction at point A, as well as friction at point B. This friction and normal force, these are going to be perpendicular at A, same thing at B. And now as I move to the next one, it has to be equal and opposite. So I've already drawn the friction at B is coming up the slope and to the left. So on the second free body diagram, it's going to come to the right. Now the goal of positioning this block is to raise it, so impending motion of the block and the wedge is going to go up the wall, so friction is going to resist that motion up the wall, and the friction is going to hold it back down. So let's see here. How many equations, how many unknowns? In FBD1, I have on the right-hand side, I want to start here because here I have an input. So on the right-hand side, I only have two equations. I can only sum forces in x and y. And I have 4 unknowns. So with 2 equations and 4 unknowns, I need 2 more equations. We want to know the smallest force P. So the smallest force is going to be what gets us just over the edge. So we have impending motion at all surfaces. Because I can't slip at one surface and not have the other surfaces also slipping at the same time. All right, so we're going to get plus 2 friction equations. Plus 2 F max equations. And they'll give us 4 equations for 4 unknowns. Now when I come back over to the other side, I have 2 equations, 3 unknowns. I've already solved for the normal force at B and the friction force at B. I have 3 more unknowns, and I get 1 F max equation. It's better to start with the input value, so the 400 pounds. So I'll start on the right-hand side. We are missing a few things in our free body diagrams. Given the number of forces and the directions, we're going to stick with just an x and a y axis, which means I need to know some of the angles down here. So the friction is along that 10-degree angle, and the normal force is perpendicular to that. So its 10-degree goes to the vertical, not to the horizontal. All right. FBD2. Sum of the forces in x equals 0. So we've got the normal force, MB, sine of 10, plus, these are both pushing to the right, FB, cosine of 10, minus the normal force at C. That all equals 0. I also have the force at B, which is max, it's slipping, impending motion, equals the coefficient of friction, which is 0.25, times the normal force at B. So there's two equations, three unknowns, some forces in Y. We've got the normal force at B times cosine 10 minus the friction force at B sine of 10, because it is pointing downward, minus the friction force at C minus 400 pounds. So we added one new unknown, and we say that the friction force at C max equals that coefficient of static friction, 0.25, times the normal force at C. Okay. And there's our 4 equations and 4 unknowns. Through the magic of time, I've written these 4 equations into a matrix down here. 4 equations, 4 unknowns. So normal force times the sine of D plus FB cosine 10 minus NC 0, 0. This one here, the max friction force, is equal to mu SN. That's been rewritten to have both sides equal to on the same side of the equation. So 0.25 times normal force minus FB. Okay. So everything's been rewritten. I've got 4 equations, 4 unknowns. When I add that into MATLAB, got those 4 equations, I build them into a matrix, I run RREF for the reduced row echelon form, and I have some values down here. So the 478 is my normal force at B. My friction force is 119.5 or 120. And you can see that that 120 is a quarter of NB. And likewise, the wall force is about 200 pounds, and the friction force at the wall is 50, or just about a quarter of that. Okay, I've made a little bit more room to work with. I've got my values written down, even though really the ones that I need here are the normal force at B and the friction force at B, because all I'm looking for is P. We'll slide over to free body diagram 1. So here's FBD1, and now we're going to write our equations from FBD1. Let's start with the forces in Y. Sum of the forces in Y equals 0. We've got the normal force at A minus, our free body diagram is not done yet. We need to have those angles in here. 10 degrees and 10 degrees. Normal force at B times the cosine of 10 plus friction force at B times the sine of 10. And because we have these values, we can actually go ahead and solve for the normal force at A. So to solve for the normal force at A, I'm going to take the normal force and the friction force at B over the other side. So I have 478.2 pounds times the cosine of 10 degrees. That's just a number. Minus 119.6 pounds times the sine of 10 degrees. Again, just a number that we can solve for. And we get that the normal force at A is going to equal 458.4 pounds. And that makes sense. It should be pretty close to the normal force in B in this case, because that's where most of that impact is coming from. I can also write here that the friction force A is going to be at impending motion, so it's going to be 0.25 times the normal force at A, or it's going to equal 114.6 pounds. At this point, if I slide up just a bit, I'm going to write one more equation. sum of the forces in X equals 0. P is pushing to the right, so that's positive, and everything else is coming from the pushing to the left. So minus the friction at A, minus friction at B times the cosine of 10 degrees, minus the normal force at B times the sine of 10 degrees. So P has to resist all of those things. It has to equal the friction force at A, or 114.6 pounds, plus the friction force at B, or 119.6 pounds, cosine 10, plus the normal force at B, 478.2 pounds, sine of 10. So P here has to equal 315.4 pounds. So 315.4 pounds. It's a little bit less than the 400 pounds, but it's probably easier for us to push sideways than it is to lift straight up. So it's a little bit of a reduction in the total amount of force to move it. But ultimately it's an easier direction to push. What that 315.4 pounds means is that as we're pushing, if we've pushed 100 pounds, nothing's happening. If I push with 100 pounds, the friction down here is not going to equal 114.6. You don't get friction from pushing nothing. But the friction down here would be solved by equations of equilibrium. So it's important to remember that because it said the smallest force P, we could use the impending motion at all surfaces to get our extra equations. As P is pushing, as it's building up to that 315 pounds, nothing's happening. As soon as you get to that 315, it just starts to move, and once it's moving, the force to keep it moving actually drops. So when you're creating wedges, don't forget the angles. Don't forget the equal and opposite. Make sure you've got a normal force and a friction force at each location. They have to share. You have to have a normal force everywhere there's a friction force. They have to be equal and opposite. You should use equal and opposite names for those unknowns, and treat those friction forces as unknowns unless you are told that there is going to be impending motion at those surfaces. And let's just finish this up with a nice highlight of the solution. Equals P. All right.